All right, so we've seen benzene rings drawn before. And the benzene ring is drawn as a six-membered ring with alternating pi bonds. However, this representation isn't exactly accurate. Okay, August Kalukli suggested that the exchange of double and single bonds was actually an equilibrium process. So those pi bonds you see drawn out are actually constantly moving, right? So much so that we actually will sometimes draw the benzene ring as a six-membered ring with like a circle in the middle to indicate that those double bonds don't belong between any two specific carbons. All right. Now, because of the nature of chapter 18 and looking at chemical reactions, we are going to stay pretty much with the usual drawing of benzene where you actually do see the double bond specifically drawn out. But we just want to keep in mind that we know that those pi bonds are always in resonance. Okay. Now, because of this resonance, which we now are going to refer to as aromaticity, benzene is much more stable than we would expect to see if the three isolated double bonds were isolated from each other and they were not in resonance. All right. So the stability of a molecule can be determined through something called the heat of hydrogenation. This basically means how much energy would it take to get rid of the double bonds in the molecule. Okay. For a six-membered ring with one double bond, it would take 120 kilojoules per mole to get rid of that double bond. So we might then expect that a six-membered ring with three double bonds would take 3 times that amount of energy, 360 kilojoules per mole. But in actuality, it takes a lot less energy. It only takes about 208 kilojoules per mole, indicating the fact that these double bonds are not only all in resonance, but that resonance makes the benzene molecule much more stable than it would be if those bonds were not in resonance with each other. Okay. Because now aromatic rings are so stable, they do not readily react. They can react, and we're going to see that in chapter 18. But they don't react as readily as a double bond that is not in resonance. All right, so you're going to see this in Argo 2, but double bonds, isolated alkenes, can undergo addition reactions very readily. We can see right here as an example, an alkene undergoing an addition reaction with bromine. All right. When we try to treat a aromatic compound with 3 double bonds with simply bromine, nothing happens. All right. It's too stable. Those double bonds are in resonance. It doesn't react. We have to kind of up the ante and make compounds that are a little bit more higher in energy if we want to get benzene rings to react. Okay. Now, one thing I'm going to point out right now, and you'll see this in the next video, is that not every ring with alternating double bonds will have this aromatic stability. All right. Some fully conjugated cyclic compounds, meaning that you have a cyclic compound where every other bond is a double bond, are actually much more reactive. They're actually much higher in energy than we might expect. And in the next video, we're going to talk about why that is, what makes a compound aromatic, and what makes a compound what we will call anti-aromatic. And then finally, what would make a compound neither one of those two things.